AI can forge identities, quantum computers threaten today's cryptography, and our systems are more interconnected than ever. In this course, you'll learn how to design blockchain-based architectures where trust stays verifiable, auditable, and resilient as these threats keep evolving. In Web 2, we mostly defended a fortress, hard perimeter, trusted admins, and the ability to patch or roll back when something went wrong. Most internals were opaque to outsiders. Web 3 reverses that model. The system is open, transparent, and composable. That's powerful, but it means your code runs under constant public scrutiny, and every contract becomes a building block for complex, multi-step attacks. There's no global undo button. Immutable mistakes, exposed keys, or flawed incentives can be exploited collaboratively and at scale. Designing for verifiable trust starts from accepting these new rules. Traditional stride threat modeling still applies to blockchain systems, but it misses two critical dimensions: incentive misalignment and governance capture. In decentralized protocols, many attacks are actually rational economic behavior against poorly designed incentives, such as reward exploits or manipulative MEV strategies. Governance is another primary attack surface. Vote buying, cartel formation, and malicious proposals can subvert the protocol without touching a single private key. A realistic threat model for verifiable trust must therefore cover technical exploits alongside consensus and governance-level failures. When we talk about blockchain-based trust, we're really standing on four shaky pillars. At the base is consensus. If validator incentives misalign, you see 51% attacks, censorship, or protocol capture. On top of that, smart contracts can be perfectly signed yet still exploitable through logic bugs, reentrancy, or broken upgrade patterns. Oracles and bridges extend trust outward, but every cross-domain link becomes a prime target for data manipulation and routing attacks. And governance is the human layer above it all. Vote buying, rushed proposals, and treasury drains can undo any technical security underneath. Think of threat modeling as a repeating tactical cycle, not a one-off workshop. Start by defining what actually matters: funds, keys, system reputation, and user privacy. Those are your crown jewels. Then map the boundaries around them: nodes, bridges, wallets, oracles, and any external dependencies. Next, systematically identify threats using something stride-like, but extend it to include economic and incentive attacks. Finally, prioritize with a risk matrix, combining impact and probability so you know what to fix first. And rerun this cycle at every meaningful upgrade. Risk isn't a snapshot, it's a timeline. Today, AI acts as a speed amplifier. It industrializes automated exploits, scales social engineering, and uses pattern analysis to mine logs, code, and user behavior for weak spots. That mostly stresses your operational defenses and human processes. Quantum computing is different. It's a horizon event that can suddenly break core cryptography, like RSA and ECDSA, exposing long-term keys and any data recorded today. Designing verifiable trust systems means handling both curves: fast, adaptive AI attacks now, and deep cryptographic breaks later. AI-driven risk isn't a single problem, it's a stack. At the code level, assume continuous automated fuzzing and exploit generation. Anything even slightly fragile in your smart contracts or APIs will eventually be hit. At the human layer, deepfakes and personalized phishing target your operators, signers, and governance processes, bypassing out-of-band checks you thought were safe. At the system level, AI optimizes MEV, oracle manipulation, and cross-domain attack paths. So treat AI as an adaptive adversary and refresh your threat model and risk probabilities on a tight, recurring cadence. Harvest now, decrypt later changes how we think about time and security. Attackers don't need a working quantum computer today. They just need to copy your encrypted traffic and ledger data now, then wait until the math breaks. That's dangerous for anything long-lived: blockchains, medical records, legal archives, key backups. Even if your crypto looks strong today, you have to design as if future decryption is guaranteed and plan backwards from that. It helps to think of risk in three dimensions: how bad it is if it happens, how likely it is, and when it's likely to matter. In the near term, 0 to 2 years, your main exposure is operational: AI-assisted attackers, misconfigurations, poor key management. Here, you tighten controls and add verifiability using today's tools. In the midterm, 3 to 7 years, you prepare for cryptographic agility. Inventory where crypto lives, design upgradable protocols, and introduce hybrid or PQ-ready patterns. For the long term, beyond 8 years, you assume serious quantum capability and even AI-driven protocol disruption. That horizon demands redesign, not patches, so you start baking flexibility in now. Treat your roadmap as 3 overlapping tracks, not a single deadline. First, stabilize what you have. Close critical vulnerabilities, harden governance, and get serious monitoring in place so you can actually see attacks and misbehavior. Next, refactor for crypto agility. That means modular cryptography, upgradable contracts, and defenses that assume AI-augmented attackers. Here, you're buying flexibility. Finally, plan for post-quantum migration and deeper redesign, new signature schemes, new identity models, and potentially autonomous agents. Each phase should leave you safer and more adaptable than the last. In post-AI, post-quantum systems, the real moat isn't a clever protocol, it's governance. Think in 3 loops. First, emergency response. You need predefined levers like protocol pauses and migration runbooks, with clear authority for who can pull them and how they're audited. Second, continuous assessment. Treat risk like an evolving metric, not a checklist. Monitor chain health, AI-driven attacks, key compromise signals, and stress test your assumptions. Third, culture and disclosure. Normalize vulnerability reporting, cross-functional reviews, and public postmortems. Effective defense is the ongoing choreography of these loops, not a one-off engineering milestone. As you design verifiable trust systems, treat this as your operating doctrine. Expand your threat models beyond code to include economics, governance, and incentives. Continuously assess how AI acceleration and quantum timelines affect your risk window. Architect for cryptographic agility from day one, then lock in clear governance for emergency upgrades. In this space, nothing is static. You're really engineering adaptability.